assessing performance is through permutation testing. So we learned about permutation testing in p-values, where you randomize the labels. You can do the same thing. Instead of univariate data, remember we're working with multivariate data. So the points on your PLSDA cluster are now relabeled. So it's not a table of points, it's a cluster of points. So what we're seeing in the first set, we have our unlabeled data. Now we've got the labeled data, the red and the blue. If we run our data through the PLSDA classifier, we can see that the red and the blue are nicely separated, and they have a separation coefficient of 12, which is very good. If we then randomize our labels on the next case, where we've permuted the data, you can see it's still the same cluster, but now the reds are different and the blues are different. We run it through our classifier, and we find that the classifier actually doesn't separate anything at all. So we can measure the separation, and basically it's very small. We can repeat the same permutations. We can run it through the same separator or classifier over and over and over again. And we can repeat the process of the relabeling and the separation by the classifier thousands of times. And then we can plot out the separation values or separation scores for all 1,000 different examples. And we can determine how many times any value has exceeded the separation score of 12.1 that we got. And we can see, at least from the plot, that essentially no models actually approached the separation score of 12.1, or no relabeling or permutations approached it. So this tells us that if we did 1,000 relabelings, that the significance of this separation is 1 in 1,000, or better than 1 in 1,000. And that suggests that this is a very robust model, very robust predictor, and we can have high confidence in the clustering that we're seeing. Now, in addition to analyzing the quality of a PLSDA plot and how rigorous or how well validated it is, we can also extrapolate other information from PLSDA. And one of these is using what's called the variable importance in projection plot. And this allows you to look at individual components, in this case individual metabolites or genes or proteins, and how much they contribute to the PLSDA model. In some respects, the VIP plot is similar to a PCA loadings plot. The weights or the values correspond to the percentage of variation explained by the PLSDA component in the predictor or in the model. As a rule, if a VIP value is greater than 1, generally 1.5, that's generally considered important. If the variable or VIP value is less than 1 or 1.5, it's generally less important. So here are some examples of VIP plots taken from different PLSDA studies. And we can see on the study on the left that acylcarnitine C3 and C4 and carnosine have values of 1.5 or higher. And so these are important features, important metabolites. On the plot on the right, we can see that carnitine, 4-hydroxypuric acid, and creatine are also all above 1.6, 1.8. And so those would also be important or highly informative features. So in that way, a VIP plot allows you to pull out important metabolites, just the way that the scores plot can also do that, or rather loadings plot. So PLSDA isn't the only tool that you can use for supervised classification. There are things like SIMCA, soft independent modeling, OPLS and OPLSDA, orthogonal projection. There are machine learning techniques like support vector machines, random forest, naive Bayes classifiers, and neural nets. These are all available and useful, and are more frequently being used in metabolomics. So at this point, I think it's important to summarize what we've learned as regard to statistics in metabolomics. Um, in terms of the statistical goals for metabolomics, typically you want to, first of all, identify significantly different metabolites between two or more groups of patients or subjects. So through that, you can use p-value or t-tests, false discovery rate corrections, q-values. If you're doing 3 or more groups, you can use the f-test. So from there, you can get potentially significant metabolites. Then from your data set, if you're looking at 2 or more groups or subjects, then you can see if these things are separable by metabolite readings. This is basically an assessment of, is metabolomics telling you anything about the biology of these 2 different cohorts? If you don't see any kind of separations, then it might suggest that the metabolomics is not what you want to use. If you are seeing striking separations, then this is certainly telling you that metabolomics has a lot of information. From the PCA, you might identify those clusters or groups of subjects that are clearly separable, potentially because of the metabolic differences. And then from there, you may also want to start coming up with ways of classifying or creating classification models so that if you were to get brand new subjects and measure them, that classifier would be able to distinguish them as cases or controls or sick or healthy or treated or untreated. And so this is one of the first steps towards developing a biomarker or biomarker panel. And this is where PLSTA is quite powerful. So these are the typical goals of statistics in metabolomics, and I've tried to highlight the approaches for each of them over the last 130 slides or so. Now, when you are thinking about statistical analysis, you might think about it in terms of trying to clear a fortress or a set of walls and how to break down this complex set of data and to get to your goal. The first approach is to use simple unsupervised methods. We talked about t-tests and ANOVAs. We also talked about clustering and PCA, which are essentially equivalent. This might be thought of just trying to launch a catapult to see if you can knock down the wall and reach your goal. If those methods don't yield anything that's compelling, then you can start using supervised methods. This is like going from the catapult to the cannon. These are a little more powerful. They're certainly more effective at knocking down a wall. PLSTA, partial least squares regression, linear discriminant analysis are certainly powerful statistical methods. If those still don't work, you can bring out the big Bertha guns. And this is where you're using things like machine learning, support vector machine, neural networks, belief nets. These are even more powerful to help extract or interpret or analyze your data. But there should be a progression. And typically the progression is always begin with the unsupervised methods, used PCA and clustering and t-tests and f-test to see if either natural clusters form, if there's statistically significant metabolites that distinguish things. Work with unlabeled data. Don't bias it. If you start seeing some trends, you're noticing some things that are significant, then you can start bringing in the supervised methods. You can also start bringing in supervised methods if it's still unclear, that the unsupervised methods are maybe giving you confusing or non-obvious results. With the supervised methods, you have to make sure that they are tested and that they are validated and that they are not overfitting. You can confirm if the clusters that you're seeing and the classifications you're making are real by testing the R-squared or Q-squared or permutation. Supervised classification like PLSTA or other machine learning methods are very, very powerful. They learn from experience, they generalize from examples, they perform pattern recognition. Because they're so powerful, people have a tendency to skip the PCA or clustering or statistical methods and to jump straight to the supervised approaches. By doing this, you can potentially expose yourself to errors. You can get great separation and assume your job is done. If you haven't done significance testing, if you haven't done permutation testing or cross-validation with R-squared or Q-squared, you could be sinking yourself into a deep hole or crossing on thin ice. As a rule, if the separation of clusters or groups isn't obvious by eyeballing, then you may be treading on thin ice. Trust your intuition. Remember, statistics is the mathematics of impression or intuition. So what this last 2 hours has been about is to try and provide you with a non-mathematical background to statistics for metabolomics and other omics sciences. The math behind these methods is actually quite hard. I didn't want to dive into it, but I also wanted to emphasize that you don't really need to know how to do the math because computers exist. And so what I'm going to show in the next lecture is how you can use many of these very powerful statistical methods through the web using a point-and-click interface through a tool called Metaboanalyst. So thank you for listening, and hopefully this has been helpful.